All right. Thank you so much for your introduction. This is Roberto Colina. I'm postdoc at Stanford University postdoctoral scholar, working in the Stanford Synchrotron Radiation Light Source in the SLAC National Accelerator Laboratory. And I will present my talk is related with X-ray absorption and ray emission spectroscopy studies on the Apollo samples core 73002, I mean the upper part of this double dry tube. So basically, I will start focus on my main goal. It's quite important to start that. Well, our main goal here is determine the oxidation state of the major components. So I will be focused on iron, titanium, but also I will be performing some investigation around silicon and oxygen. So this is in the context of space weathering. Remember that space weathering describes all the processes that occurs on the moon, such as micrometeorite bombardment and all the physical, chemical, and spectral effects that occurs, such as glutinate formation, but also sublimation and contamination. So that we need to take into account. So here I have a couple of pictures about some preliminary results from other works. So some investigators have reported the presence of iron nanoparticles on the regoliths, but also we have information about the presence of agglutinates on the regoliths. So how one of our question is try to understand how the regolith mature, but also what happened with the metals on the moon. We have more reduced or more oxidized species. So it's very interesting to understand all the chemical processes in the lunar regoliths. So for this, I will be using software ray spectroscopy, but also some tender ray emission analysis, focus again on oxygen, titanium, iron, and silicon. We have a set of different tasks. We started this project, this part of the project, performing some laser irradiation on simulated space weathering minerals. So we collected data on this simulated space simulants, and also we have performed some data collection on the electron energy loss spectroscopy side, that is like the electron-based analogous. So this project also involves some ab initio calculation using density functional theory to get more information about the ray spectroscopy features that we can get from the experimental spectra, and everything we repeated for the NASA post sample. We have received some of them from the upper part of the double dry tube. So in particular, we have 4 different samples for different depths, that also from other teams in the ANGSA project. We have an idea and estimation about how about the abundance of iron, that is around 7 and 8%, but also we have an estimation about the titanium abundance in our regolith, that is around 1 and 2%. And also we have information about this ferromagnetic index that give you information about the maturity of our soils. So we have this 4 samples from the recently opened tube, but also we have received some samples from previous open samples that I've been calling like the old samples here. So briefly, we have performed this array spectroscopy studies at SSRL here in the National Accelerator Laboratory. So to study iron, titanium, and oxygen. So XCS is a photon in, photon out for level spectroscopy that basically improve the chemical environment around a certain species. So it's an element-specific technique. So we were proving the unoccupied electronic states around around our species. So it's very powerful because we can get information about the local coordination environment and also what are the oxidation state of the major components that we have on the regolith. So I started studying the iron LH. Basically, from the iron LH, we get information related to electronic transition from 2p state to unoccupied 3D electronic state. So here on the left, we have our results for our 4 samples that we already have. It's quite important here to compare with some standards. For example, here we have a standard for metallic iron, but also iron 2 plus and iron 3 plus. So basically, these features qualitatively point that we have that the predominant species is iron 2. So it's reduced in comparison that probably we are expected to get here in the moon, here in the Earth. Sorry. So this is consistent with we are expecting, but it's quite important to mention here, and it's very interesting that we have some features related to metallic iron. So this could be related with previous observation about iron nanoparticles in some immature soils. So also we have obtained a relation between the maturity and the presence of these metallic iron features in our spectra. So we are pointing that, well, probably we have getting information about this iron nanoparticles that also could be in a core shell configuration. So in the future, we pretend to perform some calculation about around this nanoparticles to corroborate if these features correspond to this kind of structure on the regolith. So we compare this new samples data with the old samples. We have obtained for the old sample features related to iron 3. So probably this is an average. In average, we have that the old sample are like a more oxidized in comparison with the new one. So this allowed me to conclude that probably iron is very suitable to reagent because this sample were open long time before. From titanium, that this is very interesting to mention here because titanium we have titanium very low concentration. So we started analyzing or trying to match our spectra with titanium dioxide in the anatase phase. So, but we have a very interesting feature here in the peak B that in our 73002 samples, we don't have this split. This split is related with reduced symmetry. So I was exploring different candidates that have a reduced symmetry in this particular direction. So I started with ilmenite. The ilmenite is have the same coordination, but the first coordination shell is oxygen around the titanium, but we have a larger distortion and also the effect of the iron. But this spectra match very good with the second peak here that correspond to the EG transitions. So in average, we are pointing that maybe we have some ilmenite-like signatures instead that the anatase. So this is one of the first candidates I have been working on. Comparing the new samples with the old sample, this is in agreement. That there, so it looks like the iron, the titanium 4 plus is less suitable to agent or or be affected for time. So from the oxygen, also we perform this reabsorption spectroscopy measurement here at SSRL. There is a huge difference in when we compare the new samples with the old ones. So this pH peak here around 533 is very strong from the new samples, and also match very good with the quartz structure. But the old samples present this splitting in the T2G and EG transitions that also could be related with we already obtained from the iron, that is like we have more oxidized iron in the old sample in comparison with the new ones. So in conclusion, oxygen looks like it's pointing to that we have quartz like spectrum signature, because we aren't observing this splitting. So this is something that we were expecting, that we have silicates in our major component here. So from the
Roberto, we're asking you to finish up your talk.
Yeah, finally, from the re-emission, we have corroborated again that we have signature about silicon-oxygen bonding and also reduced species. My concluding remarks, basically, this is a powerful technique to study an element-specific local electron structure in our samples. So we have certain signatures about ilmenite from titanium, but also iron is very suitable to be oxidized and reduced. Well, thank you so much for attending to my talk. Your questions, comments, and suggestions are very welcome. Finally, I would like to acknowledge to all the team, including my advisor here in SLAC National Accelerator Laboratory, Jeff, that is the main PI in this ANGSA mini team, but also Hope and all the collaborators, well, even all the people involved, Chip, and all the teams that have been working in this, also for funding my postdoc. Thank you so much.